Next, we're going to look at an example of the derivative of logarithmic functions to sound intensity and loudness. So first, a little bit of background on how sound intensity is measured. So first of all, sound intensity is a measure of power per unit area. So power is energy per unit time. So it's measured in watts per meter squared. So if you imagine just a screen and you have sound waves coming from some sort of source, and then they're passing through this screen. So you have like a flat piece of area in space, and sound energy is passing through that piece of area. So sound waves carry energy. So the louder a sound is, the more energy it carries. So, and also, if you carries energy, a certain amount of energy by itself doesn't accurately describe the intensity of the sound. If it carried so many joules of energy, well, how long does it take for that much energy to be transmitted over a piece of space? Or how long will it take for that much energy to be absorbed by your eardrums? The same amount of energy being released over 10 years versus over 5 minutes is going to produce a very different effect. Right? Over 10 years, that energy is dissipated so that it only trickles out a little bit at a time. You might not even hear it, it might not even be audible. But if that same amount of energy is released over a second, it could be a very loud, deafening bang. So watts, 1 watt is equal to 1 joule per second. So this is the watt, and then 1 joule per second. So 1 watt is equal to 1 joule per second. Joule is the unit, the SI unit of energy, so it's basically a measure of energy per unit time. Now you can have a certain amount of energy, and this is called power. So power is energy per unit time. So it's basically the rate at which you're delivering energy. Now you've got it, power is the time derivative of the energy. So you can think of this as a derivative because it's a rate. But also note it's not just watts by itself, it's watts per meter squared. So the idea is you might have so much power, sound, so much energy per unit time that you're being released, but close to the source, let's say you have a speaker down here, close to the source, all that energy is going to be passing through a very small space. And as you move out, that energy gets dissipated over a larger and larger space, right? So it radiates outward. So the sound intensity is going to be weaker over here than it is close to the source. You've all experienced this. If you're standing next to a really loud speaker at a dance club, it can be quite loud, but at the entrance door it's not as loud. Outside in the parking lot it's not as loud, and so forth. As you move farther and farther away, the sound level gets weaker and weaker. And this goes off as the inverse square. So basically sound intensity is proportional to the square of the distance to the source. So R is the distance to the source. And the reason this works like this is because sound waves travel, they radiate in spheres. So since the surface area of a sphere is proportional to the radius squared, if you're twice as far away, the surface area is 4 times as large. So it's that same, it's because of the surface area of a square goes like, or of a circle, of a sphere, surface area of a sphere goes like the radius squared. It's for that reason that the sound intensity goes inversely proportional to the radius squared. So basically it's always the same amount of energy, but it's either over a small sphere or a larger sphere, so it's being dissipated over a small space or the larger space. So, but it's proportional, inversely proportional to the radius or the distance away from the source squared. Now, sound intensity can come in a whole, there's a wide variety of different magnitudes that describe sound intensity. So a benchmark sound, which is what we call I sub 0, is 10 to the minus 12 watts per meter squared. This is right about the human threshold of hearing. But then as the intensity grows, you're going to see a wide array of different orders of magnitude. Something that's 10 times as strong, 100 times as strong, 1 million times as strong, 1 billion times as strong, 1 trillion, and so forth. So you get these huge array of different orders of magnitude, and it's very hard to keep track of something that's, this level or this gigantic level. So to actually measure the loudness of a sound, we use something called decibels. So a decibel, so the sound loudness, L, measured in decibels, or decibels, dB, is given by 10 times the log of I over I naught. So this is the sound level of a sound with intensity I. So it's basically you're looking at the ratio between the sound intensity and this benchmark. This is basically a standard benchmark sound. So if you're 10 times louder than the human threshold of hearing, so if I is equal to 10 times the human threshold, so the intensity is 10 times as much, we get log of 10, which is just equal to 1, so that results in a loudness of 10 decibels. If you're 100 times, so if the sound is 100 times as intense as the threshold, we get log of 100, which is equal to 2. So the loudness is 20 decibels. If you are 1 million times the benchmark, we get log of 1 million, which is equal to 6, so that would be 60 decibels. So in this way, so 60 decibels might be standard conversation, 80 or 90 decibels might be a vacuum cleaner, 120 decibels might be the sound of a jet engine, and so forth. So you can see that even though the actual intensity ranges over, vastly different orders of magnitude, the loudness is, it's easier for us to understand, that's 60 decibels, that one's 80 decibels. So 80 decibels is 100 times the sound intensity, 100 times the power as something that's 60 decibels. 90 decibels is 1,000 times the power as 60 decibels, and so forth. Something else that works on a logarithmic scale is the Richter scale with earthquakes, except there's no factor of 10 there. So for example, a 5.0 earthquake releases 10 times the amount of energy as a 4.0 earthquake. And then a 6.0 earthquake releases 100 times the amount of energy as a 4.0. And a 7.0 is 1,000 times the energy of a 4.0, and so forth. So the Richter scale is also a logarithmic scale in a similar type of thing. So first, for this problem, let's take the derivative of the sound loudness with respect to the sound intensity. So we have loudness is equal to 10 log of I over I naught. Now, we know the derivative of the natural logarithm, but we don't know the derivative of the regular logarithm, which has base 10. So first we need to explore that. Well, recall that the log of x is equal to the ln of x divided by the ln of 10. So this is one of the basic log rules. So basically, it's more general. Log, base b of x is equal to ln of x over the ln of b. So since the standard log has base 10, this is the same as saying 10 over the ln of 10 times the ln of I over I0. Now, we can differentiate this just using the derivative of the ln. So the derivative of a natural logarithm is always the derivative of the inside function divided by the original. So the inside function here is I over I0. So the inside function is I over I0. So the derivative of that is just going to be 1 over I0. So I0 is a constant and I is the variable. So if we take, d by di, I over I0 goes to 1 over I0. So the derivative of the inside is just 1 over I0. So this is the derivative of the inside. So recall that whenever we have ln of u of x, the derivative is u prime of x divided by u of x. In other words, the derivative of the inside divided by the original inside. So the derivative d by di of our function 10 over ln of 10 ln of I over I naught is equal to, well, 10 over the ln of 10 is a constant, so that just gets swept along for the ride. So the derivative of the inside, which is 1 over I naught, divided by the inside, I over I naught. Now the 1 over I naught in the numerator and the denominator cancel. So this one cancels with that one. So we're left with just 1 over I. So basically dl di is equal to 10 over I ln of 10. Just like that. Okay, so let's record our results so far. So we had the formulas. Loudness was 10 times the log of I over I naught. The LDI was equal to 10 over the intensity times the ln of 10. And then we also had I is equal to some constant over R squared. So now let's replace I with this function k over R squared. And instead of viewing it as L of I, let's do L of R. So L of R is going to be 10 log of k over I naught R squared. So this is for a particular source, and now we're looking at the loudness measured in decibels, in other words, the sound level measured in decibels, as a function of your distance to the source. So instead of saying, what's the rate of change of the sound level with respect to a change in the intensity, that's dl di, we're now saying, well, what's the rate of change of the sound level in decibels with respect to distance? And also note that dl di has units of decibels per watt, and then I is watts per square meter. So it's decibels meters squared per watt. So those are the units of dl di. The units of dl dr are going to be decibels per meter. Right, because it's a change in the sound level and measured in decibels per unit space, so per meter. So the derivative of this, again, we want to rewrite this as 10 over ln of 10 times the ln of k over I0 R squared. Now, this is equivalent to 10 over ln of 10 times the ln of k over I0 minus the ln of R squared. Right, so using the log rules, right, log of a over b equals log a minus log b. We just broke this up. Now this one's a constant, so the derivative of this term is 0. So dl dr is going to equal, I'm going to take the minus sign up front, minus 10 over ln of 10. And the derivative of ln of R squared is equal to 2 over R. So we get minus 20 over R ln of 10. There are two ways to see that. So when taking the derivative of ln of R squared, first we can note that that's equal to 2 ln of R. So therefore the derivative is just going to be 2 over R. On the other hand, we can do this rule where we say it's the derivative of the inside divided by the inside. So it's 2R, that's the derivative of R squared, divided by R squared. Well, here, one factor of R cancels out, and it's equivalent to just 2 over R. So either way, the derivative of this is 2 over r, so I get 20 over r. We get the minus sign here over ln of 10. And then this term is all a constant, so its derivative is 0. So dl dr is minus 20 over r ln of 10. So let's move that back up top. So the LDR was equal to minus 20 over r ln of 10. Now what we're going to do is we're going to look at the LDI, the IDR, and compare those two with the LDR. So I of r is right here. So the IDR is just the derivative of I with respect to r. This is r to the minus 2, so it's equal to minus 2k over r cubed. So the IDR is minus 2k over r cubed. The LDR was this one. So let's write these ones out. So the LDI was this, 10 over I ln of 10. But what I'm going to do is I'm going to replace I with I of r. So I was k over r squared ln of 10. So this is the LDI expressed as a function of distance, but it's still dl di. Now the IDR is minus 2k over r cubed. And then finally, the LDR was, we computed as minus 20 over r ln of 10. Now you'll notice that if I multiply the LDI times the IDR, I obtain the LDR. So when I multiply these out, the LDI times the IDR, I get, well, the LDI is 10r squared over k ln of 10, and then times, the negative sign I'll move up front, but times 2k over r cubed. So the k's cancel. So the k here cancels with the k there. The r squared cancels two of those, and so it's just equal to minus 20 over r ln of 10, and that's equal to the LDR. So we see that the LDI times the IDR is equal to the LDR. Now this isn't just a coincidence, this is an example of something called the chain rule. So even though we haven't introduced it yet formally, this is a manifestation of a rule that we'll study in depth later on. But it's nice to kind of see it in action before we get bogged down with the theoretical aspects of it. So that is sound intensity and a variety of interesting ways of looking at those equations.